Okay, so in this video we will be covering the question Berkeley Bites Buffet. You are the proud owner of Berkeley Bites Buffet and business is good. You have a policy where children under 8 eat free and seniors eat 50% off. Since you're a savvy business owner, you keep the ages of all your customers. For taxes, you must submit a list of the ages of your customers in sorted order. Define age sort, which takes in an int array of all customers' ages and returns a sorted array. Assume customers are less than 150 years old. So in this question, we basically have an array of ages. So let's say the ages are 4, 14, 63, 72, 14, 20, and 63. So given this list of ages, we want to return the same list, an array, that's sorted. So off the bat, what we know is that we can use sorting algorithms like quicksort and merge sort. And these give us a running time of n log n in the average case. But can we do better than n log n? So the first thing to notice is that our max age is 149. So we can go all the way from 0 years old to 149 years old. So if we consider this our radix, then we have 149 or 150 symbols in our radix. You can call it a radix or you can call it like an alphabet. But because we have this alphabet, we have this constrained set that we're going to be choosing from, we can use counting sort. So here's the basic procedure of counting sort in terms of this problem. So what we will do is we would have like an array from 0 to 149. So this is the indices. So you go like this, and so on till you get to the end. So this will be our age counts array. So what we're going to do is we're going to take this array that we have, that we start with, and we're going to go through it, incrementing the count of each age that we see. So the first age we see is 4. So I'm going to increment the count from, assume all these are zeros. So I'm going to increment it to 1. And then somewhere along the line, we'll come across 14. I'm not going to draw the entire 150, element array here. 14 will increment that to 1. And then we'll get 63 somewhere along here. And we're going to increment that to 1 as well. And then we'll hit 72. That'll be somewhere after 63. We'll increment that to 1. And then we get 14. And we've already, we already have 14 as 1. But we're going to increment 14 now to 2. And then we see 20, which is like somewhere here. We increment that to 1. And we see 63, which also was already incremented to 1, but now we increment it to 2. So a larger array, it would work exactly the same way. So now what we're going to do is we're going to use these counter arrays to build up our final sorted array. We're going to go through the entire array in like a for loop, and for each age, we're going to add that age however many times is specified in our array. So you see how I'm filling the spots that we haven't filled, so the other ages which aren't present in this array with zeros. So every time we reach, a age which has 0 in the age counts array, we're going to add it 0 times. But if it has a 2, we're going to add it 2 times. So 0 is 0 times, so we're not going to add it. We're done with that. 1 is 0, 2 is 0, 3 is 0, 4 is 1, so we're going to add 4 ones. Then everything in the middle is 0. 14 is 2, so we're going to add 14 twice. So everything in the middle is 0. 20, we're going to add once. 63, we're going to add twice. And then finally, 72, we're going to add once. So here is our sorted array. If you noticed, basically what we had to do was we went through this array once. And then we went through this array once, and we added the values to our result. So the runtime of this algorithm is actually theta of n, where n is the size of the input array, plus r, which is the size of our radix, or our alphabet, and that in this case is 150. So this, since r is constant, can simplify it to theta of n, and we see that theta of n is better than n log n. So in this problem for 6.1, the first part, we have found a way to create an algorithm that runs in theta of n time. Okay, so now let's look at the actual code. So we have our class called Berkeley Bytes. We have our maximum age, which is 149. So we first have this method, histogram, and then we have our actual age sort method here. So what we're going to do is we're going to use the histogram for creating the age counts array that I specified. So how do we create age counts? So we create this new array called age counts. So it has a size of max age plus 1. That's because we have ages 0 through 149, which is 150 in total. So it would be max age plus 1. So for each age in the ages array we're given, we're just going to increment that age's value so that it adds to the count we have so far for that age. And then we're going to return that array. So since we have the age counts array, let's see how age sort uses that age counts array. So the first line, it calls histogram, gets the age counts array. So the input is ages. And then we create this new array result. So this result is just going to be the sorted array that we return. So we start in an index of 0. So for each age equals 0, age less than or equal to max age, it's less than or equal to, not less than, just making a note there. We're going to take that age's count, so age counts age, and add that age to the result array as many times as is specified by age counts age. So basically, if an age is counted 5 times, then we're going to add that age back in 5 times, but it's going to be in sorted order this time because we are adding the ages in order. So we're going to add that age at the index we're at, and then we're going to increment the index so that for the next value we're going to add to this array, it gets input into the right index. So once we go through all the ages and all their counts of the ages, we'll be done filling up the result array and we can just return it. Alright, so now let's do 6.2. So time passes and your restaurant is doing well. Unfortunately, our robot overlords advanced medicine to the point where humans are now immortal. How could we extend the algorithm to accept a list of any ages? So the difference here is that now we don't have a max age, right? Because we're immortal. So instead of using counting sort with a radix, an alphabet of 0 through 149, we can use radix sort, such as LSD or MSD, and go through each digit of the age. So for example, so 149 has 3 digits, right? So we'd go through, 9 and then 4 and then 1, or we could go the other way, 1, 4, and 9, and go through that order in order to do LSD or MSD. In this case, the radix would be 0 through 9 because each digit can take the value 0 through 9. So when would we be able to use this type of sort? So we can use this sort when our keys that we're sorting on, So in this case, our ages have some type of base or radix. In other words, the type of the item must be some combination of symbols. In our case, it's a combination of the symbols 0 through 9. And that's it.